All right, everyone. Thank you for joining us today. My name is Casey Baker. I am with GridLab. We're a nonprofit technical support organization interested in ensuring reliability towards the clean energy transition. And we are happy to bring you today two speakers to talk about our recently released paper, Practical Guidance and Consideration for Large Load Interconnections. Quick housekeeping items: microphones will be muted throughout the duration of the presentation. The meeting is being recorded and will be made public. There will be time for Q&A at the end of the presentation. Throughout the presentation, if you have a question, please click on the Q&A button at the bottom of your screen and input your question there. And then we will also have some polls throughout the presentation that we invite you to participate in, which is helpful for us. Quick overview of why we are meeting today. So as many of you all know, large loads and increasingly very large loads are connecting to the grid, and we need to ensure that this is happening in a reliable way and in a way that is fair to all grid users. And we recognize that and appreciate the great work that the ESIG Large Load Task Force is doing, as well as the NERC Large Load Task Force and other regional efforts are doing to really drill down on these issues on the technical side, as well as the cost side and cost allocation side. At the same time, we recognize that decisions are being made today based on these large load interconnections. And so what we felt like the industry needed was a paper to come out that provided a general roadmap of many of the new considerations that need to be brought to the forefront as decisions are being made about these large load interconnections, both from a technical perspective, so what are the reliability impacts, and then from a cost allocation perspective and a utility regulatory perspective. So we're interested in speaking about that to you all today. So with that, I'm going to introduce Ryan and Kyle from Elevate Energy Consulting. Dr. Ryan Quint is the president and CEO of Elevate Energy Consulting and president and chief engineer of GridStrong. Ryan is responsible for the strategic direction and execution of Elevate projects across all verticals and is focused on building a world-class team of experts to tackle the complex and emerging challenges with Elevate's industry partners. Kyle Thomas leads Elevate's engineering and NERC/FERC regulatory compliance services division and supports the strategic direction and execution of a myriad of Elevate projects. He has extensive experience in protection and control systems, substation equipment, transmission planning, data center and inverter-based resource integration. With that, I'm going to hand it over to Ryan to please take it away. Thank you.
Awesome. Yeah, thanks, Casey. And thanks everyone for being here. We're excited to talk with you all today about the report that we put together. So yeah, Casey hit it right on the mark. I think given the speed that these interconnections are coming, as well as the connections to the grid are happening, we wanted to get useful material out there publicly to the extent possible that we could. We wanted to take sort of the lens of a broad-reaching, widely educational report. It's a lengthy report. It's almost 100 pages. And we tried to cover, kind of soup to nuts from initial interconnection, some of the risks, some of the challenges, the process, the models, the studies, the decisions, try to cover a little bit of everything so that the report can be useful and educational to a wide range of stakeholders. Now, each one of these chapters or sections or discussions that we're going to go through is a paper in and of itself, or a whole discussion or a whole presentation in and of itself. So our goal is that if you're an expert, if you're niche in one part of this process, hopefully you learn something about the other parts of the process. I know for me personally, going through this exercise has been very educational, working with Casey, some of the other co-authors, with Kyle as well. So really glad to put this together with GridLab and for y'all to be here with us. So with that, we'll jump right in. I'll hand it over to Kyle.
Thanks, Ryan. Thanks, Casey. Screen's looking good, full screen, just making sure.
Yep.
So just, of course, start with the background fundamentally of I think what many of us know now, but just to set the stage, we see this large load, and really that's driven by data center growth happening pretty much everywhere across the country. and also many other countries around the world, this growth is seeing just with the sheer demand of our usage of computing systems, of the internet, of data in general. It's driving this growth kind of fundamentally across the board. So you'll hear in various places it is exponential, in other places it's steady, straight load growth. At a time when historically we've had very little to maybe negative or 0.5%, 1% growth at most. Seeing this growth now happening everywhere is an amazing opportunity, but it's also an amazing challenge to meet fundamentally from our industry. You're seeing this in many, many hotspot regions around the country, shown on that map there. And again, fundamentally, data centers drive the large majority here. And as you're seeing and hearing this term, large loads, right? There's a lot of discussion happening at many of these industry working groups about what does that mean really holistically. And so there's a lot of different types of these large loads. Data centers is the 80% or more type of large load facility where we're seeing the biggest growth. In some of the analysis done in the Western Interconnection, it was 80% or more of the large load interconnection queue demand was from data centers alone. These are in the hundreds to thousands of megawatts per request, where we continue to see kind of news releases, announcements, where that number just kind of keeps getting bigger. We're beyond even the gigawatt level campuses or data centers. We're approaching even larger, which is just amazing and incredible to see. It's driven by, we know the largest corporations in the world are developing these, and there is speculation in some of these aspects. We're talking about that in a little bit on our process. And what we do know, though, is fundamentally that speed to construct and build these and get them connected is probably the dominant driver across the board, even maybe less so than cost. Cost is always a factor, of course, but that speed is driving more so than anything else there. Just to name some of the other types of large loads, they're all important. They all have their own unique aspects. And certainly many of the practices and discussions that we're talking about in this paper and in this presentation today are very much applicable to many of these others. It just so happens that right now, where we're at today in 2025, the data centers is the dominant source of where this growth is happening. And that's where our big focus is. But a lot of what we're doing and talking about apply to many of these others. So that includes large industrial manufacturing, even specialized manufacturing like semiconductor manufacturing. You've got the cryptocurrency mining operations. You're seeing the electrification of many industries like electrification, transportation, heating and cooling. Hydrogen fuel production is a major one, which has huge forecast of growth happening. We've seen some, but even more on the horizons. And then things like mineral mining in certain areas or agricultural loads as well are very, very large in many ways. But again, those are all the 20% compared to where the data center is just the dominant resource overall. So when you think about this growth, and we are in the middle of this growth in many areas. Some places like in the Mid-Atlantic have seen growth over the past 10 years. Others are seeing it in the past 6 months to a year. But what we are starting to see, and why Ryan and Casey entered this, we're starting to see some signals that are concerning reliability problems and say grid stability risks that are of concern, as well as other problems that we'll talk about, interconnections and cost structures and that type of thing. But we are seeing where maybe the light is being turned on of like, there are some problems that we're starting to see around the industry that put reliability and stability at risk and at concern overall. So there's been a lot of presentations and paper and ink spilled on these topics here, but there were 2 large data center trip events or disconnection events that occurred in Northern Virginia. One was in July of last year that we'll talk a little bit, and the chart on the right shows that. And then another one occurred in February. And what you're seeing in July of last year, that event was 1,500 megawatts of data centers tripping off or being reduced at that time. In February, it increased from that to 1,800 megawatts. Not a good trend. That's a lot of megawatts that are being tripped off from a grid event where, importantly, the utility wasn't expecting that to occur. And so that's a bit of operating or working in an unknown operating state, which is never ideal and very difficult to achieve reliability if you don't know these things or even have an idea that these types of things could occur. So what happened here? There was a grid fault occurred from the first one in July from a failed piece of equipment. Everything on the protection and control system worked exactly as designed, but as a consequence of that fault in that operation, 1,500 megawatts of data centers over, if you look at the bottom right from some of the NERC data and report on this event, many substations with dozens of data centers tripped offline in response to that fault. And that accumulated in 1,500 megawatts. The one in February was fewer number of data centers, but more megawatts. And importantly, a lot of what we're still learning in the industry is why did those data centers trip offline? We now know some more details is related to protection and control systems built into the site. But importantly, this is after the fact knowledge. We need to know this stuff on the grid side so we can plan, study, and operate the system on what these things happen. So these are leading indicators of the types of new problems that these facilities are introducing with some real grid events that start to raise the flag that we need to look into this further and solve some of these problems before we get into an even worse state or worse type of disturbance that causes a bigger impact to a lot more customers and grid operators. The other fundamental aspect of putting pressure, I mentioned earlier that speed is paramount across the board. And this is also driven by the fact that the data centers themselves can build their facilities faster than any other sort of infrastructure that they rely on. And they're getting better. It was, say, maybe 3 years, 4 years. Now it's definitely 2 years. And in some cases, depending on the size, it's a year. So they can build these facilities. They're getting very, very good and have gotten good over the past decade or more building these facilities. Similarly, we're very good at building transmission, very good at building distribution systems, very good at building generation resources. When we get through the complicated and lengthy process of the planning, permitting, and approval stages to get them actually built. The actual build time is quite fast. The part that's taking longer and longer in getting this nexus of a problem of it is just taking longer for us to build our core infrastructure, driven a lot by the permitting, the approval stages, and even the planning and this exponential growth of queues and analysis makes that planning and modeling part even harder. And so we have this disconnect that's representing itself in many of the challenges that we're going to talk about that Ryan will focus on in the interconnection process and policies and regulations as well here. So it's that grid reliability problem. We're seeing things, but then I think every day right now we're living this problem of this disconnect of the timelines for how fast they can build versus how fast the utility systems can get built. Utilities, generation, substations across the board there. So going a little deeper into that, I gave some of those leading indicators of those grid reliability problems with those two events. There are other types of grid reliability challenges that we are hearing about, some throughout the country and the world are seeing, maybe not as reported on as heavily, because one of the biggest problems that we're going to talk about, Ryan will talk about, is there's a lack of data and information on some of these, given the criticality of the systems, the confidentiality of these data centers. Some information is not able to get shared. But what we are hearing and seeing in some places are a whole set of some of these reliability challenges. So in a parallel to that speed question, those two charts, I showed the faint signals, and then I showed the timelines of how construction. Well, there's this fundamental balancing act between these two that we're living right now. We know the economics, they're driving a lot, and it's incredible opportunity for the system. We get long-term predictable like PPAs and load growth, revenue streams are there. We get that expansion and upgrade of our infrastructure through these projects. We see even more demand coming. We see new service models happening. It's huge economic development for the regions where these facilities are getting built, not to mention also huge job creation. And that is driving, that need to get these built very quickly, both by the sheer demand of the data center developers, owners, and operators, but also the utility side. There's a lot of positives there. And that's certainly what everyone's trying to meet. But we're trying to balance it with these grid reliability problems. How do we move really, really fast without breaking everything necessarily, without jeopardizing reliability, without answering some of these unknown questions, where we fundamentally, as a grid owner, as grid operators, we know that planning and operating the system, we need to know and be able to predict what can happen. Otherwise, we would literally be operating in an unknown operating state, planning in an unknown planning state that can introduce substantial risk for the whole interconnections, for all customers, for all owners and operators of grid equipment there. And those reliability problems, we'll talk about more, they're numerous, that we have to really understand those while we're moving really, really fast. This is things like voltage and frequency stability. How do you deal with that inundation of the interconnection queues? What are the regulatory risks and hurdles and changes that are coming? And then what about the fundamental, like, unknown operating or uncertain operating characteristics for how these new loads really will operate when they're also changing in real time as they learn and get better in this new system, especially driven by AI. So this balance act is where we're seeing a lot of problems on both sides, and we're working fundamentally as an industry to tackle both, and we're going to give guidance overall on both these aspects. If you think about one of the questions we get a lot is, we've had large loads on the system for a while. Why is this a problem now? What's different? Well, specifically for data centers, they are newer than some of our classic large loads that we've connected for the entire time of our grid, manufacturing facilities, across the board, things like arc furnaces and other sorts of very large loads. Like, we've done that forever. Data centers have been newer, and they do introduce newer characteristics and attributes that introduce new problems that we are very much learning in real time. And they're also changing rapidly as the introduction of AI and other sorts of new systems there with large language models and the like, that's introducing new attributes on top of an already fairly new type of load on the system. So we did a few of them to talk about size. They're far, far larger. I mentioned the gigawatt size campuses. That was pretty rare to see that in the past. So, and we're seeing that more and more and more. That's driving reliability upgrades, system upgrades, system impacts at a bigger scale and farther spread area than we historically saw loads causing. The load characteristics themselves, they're new, how they're operating, their demands of equipment integrity, their challenges of when they're operating things like an AI training run. How are their characteristics? What's their load profile? What's their equipment operations that will exist, and how they integrate with grid disturbances and grid dynamics? That sensitivity of those grid disturbances is another big area of concern and work that the industry is working to understand for sure, driven by a couple of those key examples of the Northern Virginia events recently. The sheer prevalence and number of requests and number of entities involved is enormous. It's overwhelming our current systems and processes. It's a very similar trend of what we saw with the inverter-based resource. Exponential growth of IBRs in the system. It overwhelmed our current structures, and now we're seeing it on the load side too. And we're working to, use those lessons learned from the IBR integration for this as well. And then I mentioned that sharing of data. In the past, you could get some of this data available about the equipment, the operations, the characteristics with the interconnecting customers, but with these data center customers, there is a criticality and a confidentiality there, given just the sheer nature of the competition in this industry globally, that lends itself to not getting all this information in the interconnection process. And maybe it's sometimes post-mortem after events occur. So we got to fix that problem as well. And we're talking about that here. So those attributes, when you think about it from all of these kind of balancing problems between the speed of interconnections and the economics and the reliability problems, right? They introduce a lot of unknown variables that are causing reliability concerns, or actually we're seeing real events start to happen. The ramping of that load, both on the millisecond timeframe, very, very fast load ramping, all the way to the ramping over days, months, and years as facilities grow and as operations change even day to day. That variability of load, that uncertainty of load, introduces a lot of operational concerns in both like stability levels, but also in resource planning and generation planning and reserve planning. Things that we have to get our real-time system to match that generation load. It just gets harder when you have more of an unknown load characteristic happening at this scale. That introduces impacts on that frequency response, voltage control. It can introduce concerns of existing generation systems. And if they're doing very, very fast load cycling, if you're thinking about millisecond level ramping and oscillations, that introduces potential risks to existing equipment. Can they resonate and cause torsional strain and damage, say, synchronous systems, where those type of oscillations we know can cause problems? Ride-through performance was the key example of the Virginia issue. Power quality problems, these very, very fast power electronic switching devices, of which data centers are pretty much dominantly run by power electronic equipment. That can introduce a whole host of power quality issues, which I'll talk about here in a second. Protection and control. How do you interface between the protection and control systems of the utility with the data center? And then, of course, your transient stability impacts across the whole system. So a sheer number of problems, all of which happening kind of at the same time, which makes this so urgent, and why we really wanted to get all this out in front right now, to just benchmark and let all of this out, in the sense that all of these problems are kind of happening, and we've got to really tackle them before we introduce any bigger concerns into disturbances. I know I'm going a little bit long. A couple examples of some real data curves from some data centers that kind of show this this cycling and this power quality problems. Right, this is only a sample of a few minutes, but you're seeing huge variations in load. And I say huge, but this is one data center. These are 5-10 megawatts that are going up and down at very, very high speeds. You're talking about milliseconds to second ramping in this type of fuzzy curves, unheard of typically before, maybe with the exception of an arc furnace. It looks a little similar there, but now you're talking about doing this at scale with many, many other tens or hundreds of megawatts collectively. But then you're also seeing different drops for unknown reasons on the utility side, that you all of a sudden went from 30 megawatts down to 5 megawatts and then went right back up in seconds later. And that's unknown and unpredicted and happening stochastically around all these types of facilities. You can imagine how this would introduce problems. And just as one example, like, we know power quality that's been around for a long time. It was driven a lot by these large loads of the past, semiconductor manufacturing and other types of large loads. Same is true with data centers, and it's introducing flicker concerns, harmonic concerns, various types of transients, and almost any other ones you're looking at here. This type of load characteristics that are occurring can cause all of these problems. And we're starting to see leading indicators that these are happening everywhere, in a sense. And we need to resolve these, need to understand this and share data to be able to mitigate these problems, ideally in the interconnection process, not after the fact, after it's already operational. So with that, we're going to take a quick second, I think, and do a poll. That's the overview of all the problems. This poll that Cassidy will throw up for everyone will say, which of these problems and concerns are your biggest and most concerning in your mind and in your region, in your system? We'll have that poll up. We'll take that, share some results at the end of this in the Q&A session overall for everyone to talk about. With that, I will hand it over to Ryan.
Awesome. Thanks, Kyle. Yeah, we can, for those that are doing the poll, I had to kind of slide my window a little bit. So if you're seeing it look a little funky, just you can pull it out a little bit and you should be able to see all the answers. Yeah, so Kyle gave an overview of some of the challenges, right? The types of issues that we're facing, why we care about large loads, why we're caring about data center loads in particular, as compared to past historical load growth, et cetera. So if we go to the next slide, what I wanted to kind of focus on is, well, what about one of the main challenges is the interconnection process, right? So not all these loads necessarily manifest, but they become an issue for the utility sector because we have to deal with them, right? We have to administer that queue and fulfill these application requests, and that's applicable to both the generation side and the load side, right? That while not everything ends up getting built, those problems are still real problems for transmission planners and the interconnection customers trying to work their way through these queues. Whether it's a queue or not, it's some logical progression of steps to get interconnected to the grid. Everyone's dealing with that as these numbers go up and up in terms of interconnection queue sizes, right? So a good example of this is just ERCOT's queue. And ERCOT's been doing a tremendous amount of interconnection of large loads over the last few years. They've got a working group that's focused on this, a lot of work. But what you see, and it actually looks really similar, if you stare at interconnection queues as a transmission planner, if I think back to my past lives, this plot looks very similar. If you had given me this plot without any other information on it, I would have said, looks like a solar growth chart or a battery growth chart, something like that, right? It's very similar in terms of there's a lot of resources going through that queue, some of which have been energized, a small fraction, the blue fraction there, approved for energization, but not yet operational. So that's what's coming. Planning studies are approved for interconnection. So there's a swath of dark purple gray down there. And then there's a whole lot of interconnection requests on the orders of many tens of thousands of megawatts of under review at the ISO level or studies being conducted at the transmission provider level, right? So those are the projects that were in the early stages of this chart, and years later, we'll probably see a chart very similar to this, where lots of applications, less actually, some going through the process, some dropping out, and eventually those that are getting connected. So lots of work is for all constituents involved in this. Let's go to the next slide. So how do we fix this, right? That's the big question, is how do we handle and manage this interconnection process? And we tried to come up with some categories of items to cover, and we'll go through each of these in more detail, but really the first and foremost is how do we safeguard existing customers, right? Through updated rates, through tariff design, et cetera. How do we make sure that everyone has access to affordable electricity and that each interconnection customer is paying their fair share for the, what they're using on the grid, essentially? That involves considering raising the barrier to entry to get into the queue, to get into the interconnection request, to submit your application. And that involves a number of items, one of which is establishing requirements. Next is building or improving a transparent and streamlined interconnection process. This is something we've spent a lot of time on the generation side. It's very transparent, and for quarter 2023 really tried to accelerate the streamlining and the speed of that interconnection process. The load side, that's a work in progress for many entities. Some entities further along, some entities have available queues and information about those queues. We get asked all the time, hey, can you help us make a connection at the utility because it's all black box and we don't know what's going on in there, right? Well, that's not the way we want to be administering queues or administering applications, right? And so bringing some transparency and fluidity to the process is definitely a helpful thing for both sides, transmission and interconnection customer. We need models. We need good quality models because those models are used to run studies. Those studies are used to make decisions. Those decisions are used to allocate costs, right? So without good quality models and studies, we run into challenges in and of itself. And then there's the whole topic of how do we fairly allocate costs and assign corrective actions to grid issues as they come up. Then we've got the construction, commissioning, testing, and interconnection aspect, right? So for those applications that have the green light to connect to the grid, how do we make sure that as they're being connected to the grid, we get the necessary information that the transmission side needs to be able to be aware of some of the risks that are presented, right? So all of the events that Kyle mentioned, right? In terms of, well, what are your trip settings? What are your protection settings? How are you behaving? What are the operational characteristics? All those things are attainable during the interconnection process or during the interconnection, build construction phase. We have to make it a point to gather that information. And if that information is not readily available, maybe we need to go back and improve the requirements to make that information readily available, right? And then once these resources are on the grid, we want to do a better job of monitoring the operational performance and making sure they're meeting any applicable requirements, right? Our faint signals should not be 1800 megawatt load loss events. They should be 20 megawatt load loss events. Gosh, I saw one data center do something funky. I connected with them. They told me they've got a protection setting set a certain way. Oh, by the way, it's set that way for all their facilities. We could have a systemic risk here. We should probably get on top of that. As opposed to, we just saw 60 data centers across a dozen substations across many different developers all do exactly the same thing, and we had no idea, right? That's the bad situation that we've sort of found ourselves in from a risk perspective, right? So we want to try to improve the effectiveness of getting out in front of some of these. Next slide. So like I mentioned, there's lots of good material out there, and there's a lot of things going on, even just yesterday, even just this week. Various entities developing some of these safeguards in terms of financial safeguards, demand charge safeguards, reliability safeguards, even environmental considerations. So things like customer paid interconnection and grid upgrade costs, allocation of the network upgrades, being really thoughtful around how those costs are allocated. Financial guarantees, getting into the queue, application fees, exit penalties, minimum demand charges, demand ratchets as the load ramps up, minimum load factor requirements, and then of course reliability requirements, performance requirements, monitoring requirements. All of these things raise the bar. So if we go to the next slide, that's a big consideration. We tried to create sort of a silly graphic here, but you can sort of think of, if we have a really low fence, we're going to get everything in the yard. Anyone that wants in, you're going to get the bunnies, and we're going to get the deer, and we're going to get all these things clogging up the queue, right? Because we don't have a barrier to entry. So in a world of speculation where we have all of these developers wanting to access the relatively minimal amount of transmission capacity that exists, you inherently create an environment where we are sort of forcing upon ourselves speculation, because we're all striving for the minimum cost to connect to the grid as fast as possible. And cost is not so much of an issue, so I'm going to throw in a bunch of applications and hope one works out, right? It makes sense given the construct that we're in with the limited transmission capacity and the easy access to capital. So what we can do is we can raise that bar, right? Not everyone can just show up and want to participate in the Olympics. You have to be able to get over the steep hurdle to participate, right? And so what that does is it weeds out a lot of the speculative projects. A lot more work goes in up front to prepare for technical requirements, have financial credibility, be thoughtful around the projects that are being submitted because the costs are higher, right? And then you're ready to play ball when that capacity is available. You're ready to play ball regardless, I'll say, right? And so you get a lot more credible customers, a lot better forecasts, a lot smaller queues. And we're starting to see that with, particularly on the generation side. So there's things we can learn and apply to the load side. Next slide. So one of the things we're really focused on too, and we were actually rather surprised by when we were doing our research, is the need to develop technical requirements for large loads, right? We're an industry where, the idea of imposing requirements on our customers is, in the past, I'd say unfathomable for many. Now we're recognizing, okay, when I connect 1,000 megawatt or a 2,000 megawatt load to my system, it has significantly more impact than most of the generators on my system, right? In terms of tripping, oscillations, power factor, power quality, all these types of things. And so, when we started looking around, there were very few technical requirements that existed for loads. We're starting to see those get built out, and entities are working on that. We're helping a couple entities think through how to build up their technical requirements for large loads in a meaningful, thoughtful, and least cost way. But it does definitely raise the bar, right? And what we saw was these requirements have existed for over a decade in Europe. There are fairly rigid requirements for large load customers in the NSOE requirements. And so, it sort of raises the question, why have we not done the same at more of the national level, at sort of the federal level, right? Do we need to protect the utilities to help the utilities to establish these requirements so it's fair and consistent across all entities? So you don't have utility one with stringent requirements and utility two with no requirements. Interconnection customers are going to go to utility two. It's easy, right? And so there's some disincentivization to create these requirements unless we have other entities stepping up to do that, i.e. some of the regulatory bodies potentially. Next slide. We started looking at, the concept of a queue is foreign to some for the load side, right? But we saw similarities in a clear and effective interconnection process, starting with an application, working through some initial screens, some feasibility studies, going through the system impact studies, whether that's cluster or not, facility studies, identifying facility upgrades. You go through the interconnection agreement, construction, post-interconnection monitoring and compliance, and then into commercial operation, right? So this looks very similar to the generator interconnection process, just with different caveats on how to treat, load customers. And each one of these, like I said, could be its own discussion item in and of itself. But for the time being, I encourage folks to take a look, read the report. There's some good content in each of these kind of subsections that talk about this in more detail. Next slide, I'll just kind of close on in the interconnection process side. I've mentioned this a few times, but there are a lot of notable differences, but also some similarities regarding generator interconnection and large load interconnection, right? And so it may be that inside the utilities, these are different shops, different different departments, different personnel working on loads versus generation. Maybe it's the same. But I encourage, particularly on the utility side, to think about how we can learn from what we've experienced with the generator interconnection process, which has a lot of experience handling large queues, lots of interconnection requests, new technologies, and how we can apply that to the other side, right? So on the generator interconnection side, we've got standardized interconnection processes with FERC Order 2023. We've got standardized modeling and study approaches with some flexibility for regional differences. We've got a first ready, first served cluster study process. We've increased the financial commitments early in the process, and we're really trying to crack down on the speculative projects to the extent possible. On the large load side, right, we have a number of entities, not all, but some entities still with rather non-standardized serial interconnection processes, not a clear, transparent process, not really clear on the types of studies or the types of models needed, particularly for interconnection customers looking to understand what their obligations are as they enter into the application phase. Lots of concerns around cost allocation. Timelines can be rather lengthy potentially because it's either inconsistent or unclear, and that's starting to lead to potential backlog, right, which we want to try to avoid. So what are the similarities? Queue management, requirements, adequate barriers to entry, commercial readiness, and standardized models and studies, right? A lot of that is we can see those needs on both sides of the fence. So if you want to go to the next slide, I'll just talk briefly about, some of the modeling and the studies work. It is a rather technical topic, but like I said, it really incumbent that we get good, accurate models and studies so we can make sound decisions, right? That is of paramount importance, whether we're in the interconnection process, long-term transmission planning, capacity expansion planning, resource adequacy, and into real-time operations, right? So let's go to the next slide. The first thing is, well, what do the data centers look like? Right? What's inside of a data center so that I can go create a model? How does the data center behave? And we presented on this a handful of times. This is an illustrative example of a data center. It's not, necessarily every data center out there looks like this. But there's all these different components that need to be considered for the different types of models we're looking at, right? Models are used to conduct certain types of studies. So we've got everything from, electromagnetic transient models, EMT models, to load flow models, to dynamics models, phasor domain dynamics models, to short circuit models. And we need to really think through, well, what level of detail, what capabilities do we have to represent these devices on the grid? And again, if it's a 50 megawatt load and it's a one-off, right, we maybe don't need to have such detailed models. But when we have large loads all over the system, interconnected right near large inverter-based resources, and these large loads are on the orders of hundreds or thousands of megawatts, we really care about the technical details about these loads because they have such a significant impact on grid reliability. So the need for EMT analysis, the need to understand what's inside the facility and how the devices inside the facility behave matter a lot, right? And so you have the PDUs, you've got cooling systems, you've got lighting loads, you've got backup generation, you've got potentially grid parallel generation, you've got filters, and then you have maybe even more advanced capabilities like battery energy storage behind the meter, or even e-STATCOMs helping smooth out some of the variability of AI loads, for example. Right. So how do we model these things? Well, first we want to know, well, what's the composite? What's in there? How do these things behave? And then if we go to the next slide, what is the composition? And there's not a lot of data out there to tell us what the load composition of a data center looks like. Now, this is some information pulled from the Western Interconnection load model tool, which is publicly available. And I think they got pretty close, right? They had done some analysis and said over the course of a days, a typical data center is mostly power electronic, 80+% power electronic load. They've got some motor A load, although most of that is used for cooling, and most of that is now power electronic connected through variable frequency drives. So the power electronic load may be even higher, But now the performance of these power electronic components are quite different. And so we have to start thinking about that more so when we get into the dynamics, the positive sequence dynamics, and then into the EMT world. So if you go to the next slide, I've kind of mentioned this already, but we have these different types of studies that are all in many ways necessary or potentially necessary to be studied because they ensure reliability, right? So for those that don't work in the modeling and studies phase, we've got, basic power flow studies. I say basic because the models are rather straightforward and easy to use, but we've got power flow studies that represent the injections and withdrawals of megawatts onto the systems. You've got generators modeled, you've got the transmission system models, you've got loads modeled. And when you're adding in these large loads, you're identifying network upgrades, you're running contingency analysis, and you're saying, hey, I want to connect this large load. Well, to do so, I'm overloading these 3 lines or these 3 components or this transformer. I've got congestion in these areas. I've got voltage problems that need to be fixed. Those are what lead to the typical network upgrade costs for some of the more early phase screenings, right? You're looking for, and these often have rather significant costs associated with them, right? When you're overloading a 500 kV transmission line and you've got to look for a solution for that, there's going to be large costs to that because that power needs to go somewhere else on other newly constructed lines or other more advanced solutions like grid enhancing technologies. And then you get into sort of the stability, the classical positive sequence transient stability study. So here we're looking for, I'm adding in large loads and I'm looking for, do I have nearby synchronous generators that are going unstable? Have I created any electromechanical oscillations, the natural modes of the system? Do I have voltage stability problems? Do I have voltage collapse issues? Do I have ride-through performance issues of nearby elements or even for the large loads themselves? So those types of studies are necessary to look for more of the stability implications. And then we've got the EMT studies, which are really rather complex, looking at rather complicated stability phenomena around controllers, phase lock loops, lots of power electronic interactions, and potentially, like I'll mention, the subsynchronous oscillations, which are very concerning for synchronous generators and nearby series compensated lines and things like that, where we see very quick instabilities that can lead to potentially very costly damages, right? And so we can't overlook the more complicated things, and those things take time and effort to make sure we get those models right. And then lastly, we have short circuit, where we're looking at breaker duty, protection coordination analysis. This becomes rather important when we're looking at co-located generation, behind the meter generation, and how that interacts with the grid, et cetera. Next slide. So just a couple solutions, for example, we're starting to hear more about e-StatComs, which are StatComs are a power electronic device that help support reactive power and voltage stability on the grid. But we provide an energy buffer behind the power electronics, and we now have the ability to inject megawatts on a very fast time scale, right? And so we're talking on the orders of milliseconds. We're able to keep up with the variability of that ramping. Now, the power supply back there is rather small relative to things like batteries. And so it's mainly there just for smoothing. It's not there for significant power injections for an extended period of time. But it can take that gray line, for example, some information Siemens provided, example of a rather jittery data center load, and we can smooth that out quite a bit with an e-StatCom. And now how much we smooth and how fast it can perform, all of that is how it's designed, how it's tuned, and then how it's sized, right? But this can be really useful to eliminate some of the subsynchronous oscillations, some of the stability concerns, as well as the ramping issues. And then on the next slide, which I think is my last slide, there's other more complicated and rather complex reliability studies that can also be considered, where you've got entire energy parks, including generation, including large load customers, and their connection to the grid, and often multiple connections to the grid across the park, and making sure that those align with the amount of transmission capacity that is being used on the grid, right? So if I'm building let's say an 800 megawatt data center, but I've only got 100 megawatts of transmission capacity, and I lose my generator or I lose portions of my data center, I've got to make sure that I'm not causing issues on the transmission system. And so we're starting to see a number of entities looking at rather complex, behind the meter solutions involving protection controls, tuning, various solutions, ESTATCOMs, grid forming batteries, and other advanced solutions to make that all work together as a unified unit connecting to the grid. So with that, I know we're a little past time, but I'll pass it back to Kyle to close us out.
Thanks, Ryan. I'll be quick on my just last couple of slides here, and it's related to some questions that we saw come in regarding, authority of these technical requirements and how do we solve this from like a regulatory aspect. So first thing, of course, when we gave some guidance here and into the regulatory aspect, both at the state level and also say federal, national level, is what questions and things should be asked. Well, everything we've just covered on these technical questions, process questions, cost questions, are all fundamentally what I think almost any regulator is looking for. Is it going to impact reliability of the customers and the grid? Is it going to cost more for all customers or existing customers? And then what is it going to do fundamentally to the system? And therefore, these questions should be asked in various regulatory proceedings, whether that's IRPs, whether it's project by project levels, and it's questions for both the data center owner and operators and the utilities. And I think everything here that we've talked about gives guidance. We have a whole section in the paper that can kind of give this overview of the types of questions to ask to the different entities throughout the various discussions going on this integration of large loads. Just to move quickly, the last question, and this is related to some of the questions here, is this question I think here is, who has the authority to put technical requirements on data centers? Is it utilities? Is it RTOs? Is it FERC? Is it NERC? Is it all of them? Great question. Today, apart from the content here, there are constructs already within the NERC regulatory standard aspect. You have a FACO 1 standard that says any transmission provider can and must actually, the standard requires, create interconnection requirements for any entities that connect to their system. Now, historically, that's always been for generation primarily. There have been various interconnection requirements that people have used for certain large load customers like arc furnaces and manufacturing and such, that they can't harm and do problems here. But that framework gives the ability for any utilities or ISO RTOs to create interconnection requirements for these new large loads like data centers. That's in existence today. But as Ryan kind of mentioned, it'd be a one-off. It'd be one-off around the country and not getting kind of this uniform standard requirements that raises the bar everywhere. And that's really where NERC and FERC could come in. And really at the FERC level, that kind of federal action would go a long way. And there's a lot happening at the FERC level within this concept of data centers and this integration and co-location questions. You're seeing quite a lot of FERC conferences here. So we know it's there, and we'll see where things happen. There are questions that we get, what about NERC? Couldn't they make NERC standards applicable here? Yes and no. I think part of, if you read the NERC rules of procedures there as just an example, it does say here, each bulk power system owner, that's not a data center provider, operator, not a data center provider, and user. That would be where the data center and large load developer, owner, and operators would really come in. They are a user of the bulk power system. And they shall comply with all rules of procedures of NERC that are made applicable to such entities. That key part there, to such entities. So presently, the problem is that within the NERC registration and rules of procedures, there is no classification for a large load customer. So until that really gets dealt with, which we'll see, NERC is very active in this space. They have the large load task force. There's a lot of work and discussions going on this exact topic at every level in NERC. But because there is no registration criteria, there is no ability, even if a new standard was written for a large load customer like a data center, to do things. There's no registration criteria, so it's a gap there. And so they are therefore not subject to any of those existing standards. But we do know that many of the standards that exist today within the SIP world, the FAC, the modeling, the TOP, the VAR, all those standards, many of those aspects would very well apply to large loads. So this is a work in progress. We know there's a lot of activity, but certainly both federal action here, as Ryan mentioned, and NERC process updates and registration criteria would go a long way to setting kind of some uniform standards across the board here. So we'll see how this develops over time. With that, I think we have about 10 minutes, Casey, for questions. And I know there's quite a lot going already here.
Thank you. And I think as all of you can tell, this is a very broad topic. And again, we see this paper as laying the groundwork to support this conversation. And again, just want to note that both ESIG and NERC are actively having conversations on many of these topics. So while we might not have a chance to answer all of the questions today, there are opportunities for these questions to continue to be investigated as we move forward. So one question we have is, shouldn't it advantage the large load data centers to share their information because an unstable grid will presumably hurt their business? Can you explain a little bit of what the trade-offs there of large loads?
Go for it, Kyle.
All right, I'll jump in on that one. Yes, absolutely. And we, have talked a lot about maybe some of the negatives. We know that the data center industry is very much working collectively with the industry. They're involved in the NERC Large Load Task Force, ESIG Large Load Task Force. They're working with all these utilities here. I think what we are seeing is an evolution of what is actually required to be shared between utilities and data centers. We are learning this in real time. And where we are really starting to realize now, after the fact of some of these events, is that, okay, some information was being shared. What voltage level, what reliability of the transmission system do you want? What's your megawatt load amount? Okay, we got all that information just to do the core work to connect something. And I'm oversimplifying what's shared there. We are realizing that we have to go to a much deeper technical level, which is, I think, a theme what Ryan and I have shared this whole time. There needs to be conversations at the protection and control engineer that's setting utility reclosing schemes and relay settings, going into the coordination of the data center protection engineers at how they're setting UPS trip set points, voltage limits, timers, and other control systems. What we're realizing now is we have to get to a much deeper level of technical back and forth discussions and sharing at that level, at the load ramping level, at their operational level, their backup generation levels that we maybe didn't know until now. But now it's like, okay, this switch is on and we need to talk about that. However, the challenge is the data center industry, that information of their architecture, their build, that is their core business. That is their core competitive edge that they're all working to, get the best performing, most efficient data centers and all these aspects that I think there's a sensitivity there that information shall not be shared and used in because now a competitive edge could get lost. I think we can get through that with various levels of protections and stuff. We are dealing with critical electric infrastructure. They're dealing with their critical infrastructure and their confidentiality. We can share that but it needs to be protected and agreements in place to get there. But I think we're learning this deep level of technical information must get shared. And we've got to get through some of these maybe contracting and confidentiality discussions, which are very difficult and part of the problem. We get through that. Now we can learn and do this deep dive on both sides on how do we actually integrate. It's exactly what we did and what Ryan spent many of his years doing with inverter-based resources and inverter manufacturers and that type of thing. We now know we need to do the same thing with data centers.
I think I'll just add, I think it comes back to the requirements, just like almost everything else, is unless you've got them established as requirements or at least just codified on paper, you need to give some runway for the interconnection customer to go get that information. And some of that information is harder to get than others, but if you aren't saying, I'm going to need this information through this process, then the interconnection customer is left blind, right? So start now. Some entities have, but when you go out and you look on Oasis or you look on, the interconnection application pages, a lot of times there's not a lot there for the interconnection customer, at least not a lot that would be needed to verify that what's being connected is and how that affects the grid, right? And so I won't go into an excruciating example, but a really good example is, most folks know how many cars you have in your driveway. What kind of cars are they? What size? Is it SUV? Is it a truck? Is it a car? How many doors does it have? Great. We can all answer these questions. These are pretty straightforward. The slightly more knowledgeable folks can tell you how much horsepower they have, right? But beyond that, it's a very select few people that you can say, well, how does your anti-lock braking system work? How are the controls tuned on your drivetrain? Everyone's going to go, I don't know. I have to go talk to the car company. That's exactly what we have going on here, is to run some of these really complicated studies like EMT analysis. It's requiring us engaging with, the hyperscalers and the PDU developers and these folks that are not readily available to the developers in every case, right? And so collaboration is key to make sure we start addressing some of the more complicated challenges. Those are the things that result in gotchas.
Great, thank you for that. I'm going to adjust the next question just a little bit. Are we aware of any regions or utilities that already have a large load interconnection queue process? And do we have any sense of whether or not that's reducing demand for large loads in these regions? Like, is it having a negative economic impact by requiring this sort of interconnection process?
Great question. I am not aware of any negative impacts yet, of any changes to interconnection process. I say yet there, we don't know and don't think. I think the sheer demand that we have in society for this load, these data centers, our use of computers, apps, AI, the internet, all that is only going up. And it's from some of the largest companies in the world that are developing these hyperscalers and more. And there are countless more being spun up to meet this demand. That even if we put more stringent requirements to make reliability, it's going to make everything better. And so far, I'm not seeing anything necessarily be a negative, like economic downturn from that in any way. I'm not aware of any, not seeing that. And we do know that there are many regions that are improving their processes in real time right now. Even this week, there's updates in certain processes and requirements that are happening in the Midwest and the Northwest. Kind of everywhere is really actively working on doing this. There's some really good examples out there that are working to address these very quickly.
Yeah, and I would just add, entities like Dominion, for example, have, significantly ramped up in the last few years the types of information, the extensiveness of the application process, the data that gets collected, and you don't see any slowdown of the interconnection process in Dominion, which is the kind of the hub for internet traffic, right? We also see the recent bills that have been passed in Texas really ramping up the the requirements and obligations on large load customers. That's not slowing down or stopping development in those regions. So, I think there are impacts, if you will, but it's definitely not stopping the flood of development opportunity observed from that community. So,
great, thank you. I think we introduced the concept of load flexibility in the paper. I'm wondering if y'all can provide just a quick introduction. I know that in our paper we introduced the concept, but this seems to be a very active place of new research. Any quick thoughts on load flexibility to address some of these reliability concerns?
Yeah, maybe I'll jump in to start. I think load flexibility, we can write a whole paper, and there are papers out there on just load flexibility, right? So we specifically didn't dive into that in too much detail in the paper. But, the conventional way that we connect loads and even generation with the FERC process is, you need to have available transmission capacity, which is based on, peak conditions and things like that, right? Most of that capacity is unused most of the time, right? And so when you can introduce the concept of flexibility to a load, you have significantly more ability to connect that load to the grid, right? Because you are able to back that load down and be flexible with that load to meet the capacity obligations under those peak conditions, right? So the grid may have thousands and thousands of extra megawatts of capacity during light days, but during those peak days when capacities are really tight, the grid is really congested, those are the conditions that define here's how many megawatts you can take. Right. And so when you introduce this idea of, under those hours, great, I'll run my batteries. I don't need that capacity during that time. I'll take it when I can get it, and I won't need it when I don't. I'll use my own generation during that time. It's extremely valuable to get access to the rest of that capacity. Now, there are regulations and policies and all types of things that need to evolve to potentially make that possible. But technologically, it's rather straightforward. And when we're in a world of constrained transmission capacity, the ability to make a load flexible, whether that's shifting, data usage, use of the actual compute power to other loads, or if it's demand response, or if it's running backup generators, or if it's adding a battery energy storage solution so that you can reduce those consumptions during peak hours, There are lots of different ways to go about that. And you can then take whatever capacity you can get from the grid and run your alternative solutions. And you then start looking at, well, how do I size my batteries? How much duration do I need? What size of my batteries do I need to be able to get through those peak conditions? And when are those peak conditions? Are they in the summer? Are they in the winter? When do they happen? Why do they happen? How do they happen? And those are all grid studies that can be done to, determine those factors.
Great, thank you. And I do recognize there's several questions in here that we didn't have a chance to get to, so I apologize for that. But I do think that this is the beginning of a conversation and a beginning of a whole host of research on this topic. So we look forward to continuing research in this and using this paper as a good starting point to facilitating these conversations. So with that, I want to thank the speakers for coming on today. And thank you all in the audience for coming on as well. And